In chemistry, the major use of phenylhydrazine is to make molecules which are known as indoles. The most widely used method to produce indoles from hydrazines is known as the Fischer-Indole synthesis. This reaction is a pretty easy way to make indoles, and it's actually quite an old reaction. It was first reported in 1875 by Fischer, which makes the reaction now over 100 years old. However, despite this reaction being so old, it's still one of the major methods used industrially to produce indoles. Indoles are generally important because they represent the core structure of many dyes and pharmaceuticals. In general, indoles are known to not smell very good, and this is exactly why I want to make them. In particular, I'm going to use phenylhydrazine to make scatol, which I'm sure you can use your imagination to think about what that'll smell like. So for this experiment, I used 8 grams of sodium nitrite, 32 milliliters of 31.45% hydrochloric acid, 4.6 milliliters of aniline, and 50 milliliters of a 2 molar stannous chloride solution. Both the stannous chloride solution and the aniline were made in previous videos. First, to a 250 milliliter round bottom was added 18 milliliters of distilled water. And then 32 milliliters of hydrochloric acid was added to the water. And then we stirred a little to mix it up well. The point of mixing the water and the acid was to dilute the hydrochloric acid to a concentration of around 20%. It doesn't need to be super precise. And then to this, with some good stirring, we dropwise add our aniline. This aniline was made in a previous video, and if you're interested on how that was done, you can check out the link in the description. If there's no link in the description, I definitely forgot to add it, so drop a comment and remind me. When the aniline is added, it should dissolve in the water and not separate out. This is because aniline, which is basic, will react with the hydrochloric acid, which is obviously acidic, and it will form a salt, which is soluble in water. Continue adding the aniline slowly and then let it stir for a few minutes to make sure that it's all reacted. It's then placed on ice and cooled down to between 0 and 5 degrees Celsius. While it was cooling, 3.63 grams of sodium nitrite was dissolved in 8 milliliters of water. It was stirred until the solution was totally clear. When it was done, the sodium nitrate solution was added to an addition funnel. The sodium nitrate solution was then added dropwise slowly. The whole time, the temperature was maintained between 0 and 5 degrees Celsius. It's okay if the temperature goes up a bit above 5, but try to keep it as low as possible. In this step, we're making the diazonium salt of the aniline. This salt is very sensitive to temperature, and heating it up too much can decompose it. Eventually, in the last few drops of the sodium nitrite, the solution became a dark orange. The addition funnel was then removed, and the solution was stirred at 0 degrees for an hour. A stannous chloride solution was then prepared in the exact same way that I prepared it in my stannous chloride video. This involved dissolving 12 grams of fresh tin in 50 milliliters of hydrochloric acid. The preparation of the stannous chloride solution takes about 13 hours at least, so this was done a day in advance. The stannous chloride solution was cooled to 0 degrees Celsius and then added to an addition funnel. The stannous chloride solution was then added slowly dropwise, again while maintaining the reaction mixture between 0 and 5 degrees Celsius. The moment the stannous chloride is added, a precipitate will appear. In this step, the stannous chloride is reducing the diazonium salt to the hydrazine. However, a lot of the hydrazine is produced, and eventually enough will be precipitated that the whole mixture might freeze. After this happened, it had to be manually shaken to stir it up. In between the additions, the round bottom was placed again in an ice bath to cool it down. Eventually, when all of the stannous chloride solution was added, the thermometer was removed and the flask was capped. It was let to stand for about an hour. After an hour, the precipitate was filtered off and it was washed 3 times with a little bit of hydrochloric acid. I then transferred it to a ghetto homemade desiccator and wrapped it with some aluminum foil. At the bottom of the desiccator was calcium chloride. Without vacuum, this desiccator really sucked, and even after a week, it was still pretty wet. I ended up using the vacuum desiccator in my lab to dry it, which did a much better job. This is what the final yield of my semi-dry phenyldihydrazine hydrochloride looked like. It can be recrystallized to clean it up, but I really couldn't be bothered. I got a yield of about 10 grams, which is actually higher than the theoretical, but this is probably because it still has quite a bit of water in it.